I'm Patrick Everett. Good evening and welcome to our Humanist group. I mentioned I'm Patrick Everett and I'm president of the Concord Area Humanists in Concord, Massachusetts, who bring you this program tonight. Before we begin our presentation, think of all our fellow citizens of the US and the world of battling the enemy, the coronavirus. We thank our doctors, nurses, hospital scientists, and others who are working tirelessly to combat this insidious disease. And we commiserate fighting it in their own bodies and who may have and also fighting it. The program events cover a wide range of topics. This is the first one we're bringing to our audience via the internet with the help of Zoom. We hope you'll enjoy it. We've come a long way in the last 10 years, starting in a small Wright Tavern belonging to UU First Parish in Concord, Mass., then in their parish hall, and now temporarily driven out of our Concord home by the coronavirus. I will now introduce Dr. Michael Mallary, who's going to discuss with us our Improbable Universe, which he described in his book with the same title. It is now in its second edition. Mike's PhD is from Caltech in high energy physics. He was an associate professor at Northeastern University. He authored 46 technical publications. Later, he moved into industry where he has 165 issued patents. These helped double computer drive capacity. He says he thus doubled the bits in the world. He also climbs rocks for fun and exercise. I give you Mike Mallary. Thank you, Mike.
Okay, thank you. Okay. All right. This evening, I'll be talking about a book that I authored in 2004 called Our Improbable Universe. It's a scientific account of how the raw energy of the Big Bang evolved into our awesome reality that we have now, where we can pretty much accomplish all the things that our ancestors prayed for to their various gods, we can do for ourselves now. But because of our addictions to fossil fuels and to playing serial Russian roulette with nuclear holocaust, we threaten to throw it all away in the blink of a cosmic eye. So in the second edition, I added appendices to discuss these down here at the bottom. The chapters in the book are shown here. The book starts off with a discussion of how the raw energy of the Big Bang first evolving into simple matter in the Big Bang, that is hydrogen and helium, in the first few minutes. And it's quite a story, even just generating simple stuff like hydrogen and helium. It's remarkable that we even have any hydrogen and helium in our universe. But then after 100 million years, this simple hydrogen and helium pulled together into large stars that cooked up complicated matter like carbon and oxygen and nitrogen and phosphorus, the kinds of stuff that we're made out of. And those large stars blew up and distributed that matter out into space, where second and third generation stars, such as our sun, could spawn geospheres, where this chemical material could get together with water and heat and produce a soup that could feed the evolution of very simple biological organisms, even simpler than this coronavirus that is presently plaguing us. Just how this happened, nobody knows exactly. It's highly speculative what exactly happened there. I'll discuss it a little bit. But somehow muck made microbes. And then after about 500 million years of, we have fossilized evidence of microbes on this planet. Then those microbes evolved as single-celled organisms for about 3 billion years. And into more complicated microbes, but they were still single-cellular. But then about 500 million years ago, there was a biological Big Bang called the Cambrian explosion. where those single-celled organisms evolved into multicellular organisms of a variety. And these multicellular organisms
Is that Jared?
move around and needed nervous systems and brains. And those brains evolved to higher levels of complexity as time went on. A particular type of critter called mammals were particularly involved with teaching their children how to live life and communicating from one brain to another. And that is our line. And so I have a chapter called Madonna and Child to show how that process began with the mother-child relationship. We're not the only animals that have this communication. Elephants also do so, and other animals as well. So I have a chapter called Elephant Spirit, followed by Human Spirit. And in addition, there are undoubtedly amongst the almost trillion solar systems out there, there are undoubtedly extraterrestrial beings out there. And the question is, what are they like? Not are they out there, but what are they like? And I do discuss those issues. I contend they actually have to be very peaceful type people or critters because they will have had to have coexisted with nuclear weaponry for a very long time. Therefore, they would have to be very Gandhi-esque in order to continue to exist on a galactic timescale. So this is a brief summary of the book. So our improbable universe, the evolution of primordial energy into mind. This evolutionary process that produced us required complex elements, carbon, oxygen, and nitrogen, a long-lived stable star like the sun, multi-billion-year environmental stability. Took 4 billion years to get from those single-celled organisms up to our state of knowledge that we're at now. For this to have happened anywhere in the universe, at least 17 physical phenomena had to be as they are. If any one of these 17 things were not the way they are, I contend it would not happen anywhere. Energy evolved into simple matter in the first few minutes, that is hydrogen and helium primarily. Big stars cooked up complex matter after 100 million years and blew up and distributed that matter out into space where it could form second and third generation solar systems. Those environments produce single-celled organisms somehow, we don't know how, out of a chemical soup somewhere. May have been here, may have been elsewhere. Multicellular beings evolved out of single-celled organisms and required brains in order to coordinate their motion. Those brains ultimately started communicating and producing collective intellect. And this collectivity of knowledge is the ultimate product of this process. It's mind-boggling how improbable it is that all this happened. Okay, this slide lists the 17 essential ingredients that I've assembled. Many physicists and scientists have identified many of these issues. I've assiduously assembled a complete list. The original version of the book only had 14. It did discuss 3 additional ones. Since between the time the original book came out and the second edition, those 3 additional issues have received Nobel Prizes, so I've upgraded them to essential ingredients as well. Okay, the top of the list is 4 forces. We have 4 forces in our reality. Gravity holds the world together, holds the Earth around the sun. The electromagnetic force holds atoms together, produces electricity and magnetism. The nuclear force holds the nucleus together so that you can have complicated atoms like carbon and oxygen. The weak force, most people are unfamiliar with, it changes neutrons into protons and vice versa. It allows complicated nuclei to be built up inside of stars. An essential aspect of our reality is that it's three-dimensional. And because of this, it's three-dimensional, it has stable orbits and intelligent life. And I'll go into that in detail shortly. One of the incredible things is the expansion rate of the universe is just right to go on pretty much forever. There's an exact balance between the expansion rate of the universe and the amount of matter in it and the amount of dark energy. If you look out into deep space, everything is moving away from us, but it's moving away from us at just the right speed so that it'll move away from us forever, as far as we can tell. And the fact that it's at just the right speed is critical to our existence. If it were moving away much faster, it would have been moving away too fast for material to clump together into stars and galaxies. If it were moving away any slower, we would have had a big crunch already. It would have all pulled together, and we would have had a reversal of the Big Bang already, and reality would have ended. Another feature that's really important is that there was just the right amount of lumpiness in the Big Bang. That is, the distribution of material was not totally uniform. If it were totally uniform, stars could not have pulled together out of the material that was there. There was a little bit of non-uniformity that allowed the stars to form out of the material that was there. If there had been a lot more non-uniformity, we would have been dominated by a huge number of black holes, and that would not have been a happy situation. One interesting feature of the universe is the fact that we have 6 kinds of subatomic particles called quarks. The neutrons and protons that our nuclei are made out of 2 kinds of quarks. It turns out there's an additional 4 kinds of quarks beyond those 2 kinds. It was essential that we had these 6 kinds of quarks because that allowed the Big Bang to produce an excess of matter over antimatter. There were other conditions that were necessary for this excess of matter over antimatter to be produced, but 6 quarks was essential. In nuclear physics, whenever we produce matter, we produce an equal amount of antimatter. Always exactly equal amount. We've never produced an unequal amount of matter and antimatter. But somehow the Big Bang produced a tiny bit more matter than antimatter at the level of 1 part per billion. For every billion particles of matter it produced a billion plus 1 of matter. In the first 3 minutes, the billion annihilated a billion, and we are the 1 part left over, the 1 in a billion. Another nice thing is that our protons and neutrons are very stable. They, most theories of what the protons would be structured like would predict protons to be unstable. But as far as we can tell, they're very stable. No one has seen a proton decay. The fundamental dynamic of all physics for small particles is quantum mechanics, and we like it that way. If it weren't that way, we wouldn't have the reality that works the way it does. The wave nature of matter is essential for chemistry and everything that we know and love. One of the important features of quantum mechanics is that 2 electrons are not allowed to be in the same state at the same time. This is essential for complex chemistry to work and for complex atoms to work. All material would act like helium if it weren't for this law, and it would be very uninteresting. This is called the exclusion principle, and it's essential for our existence. Another feature is that neutrons are just a little bit heavier than protons, just the right amount. One of the things that got me going on this whole thing, I'll talk more about it shortly, is that 2 protons stick together only very briefly. to make helium-2. Helium-2 is an unstable material. It doesn't exist in nature for any length of time. And the fact, if it did exist as a stable element, the sun would burn up in a period of 1,000 years, and we would not have time to evolve. When I first heard about this in graduate school, it knocked my socks off, and it got me started on this whole odyssey. Similar to this issue is that we don't have beryllium-8. If we had beryllium-8, then the sun could burn helium into beryllium-8 very rapidly and burn up in no time at all. It's also important carbon forms faster than it burns into oxygen. If it didn't, we'd be in a universe dominated by oxygen with very little carbon. Being carbon-based life forms, we like the fact that this is the way things work. As I mentioned before, it's important that big stars blow up and disperse their complex matter into space. Well, when you do computer simulations of big stars blowing up, unless you include everything, and I mean everything, the computer simulations don't blow up. You really have to have everything in there, and then you can get them to blow up. And so if any of these laws of physics were just a little bit different, these big stars would not blow up, and you would not get that material back out into space where it could do interesting stuff like produce people. One of the things that Hawking's did was to point out that black holes are in fact white. That is, that they decay. And that's really good because the Big Bang would have produced a huge amount of little black holes. And those little black holes would have gone around becoming bigger and bigger black holes, gobbling up everything in sight, except that they decayed. And because small black holes decay rapidly. So that was really a good thing. Otherwise, we'd be having to look over our shoulder about a little black hole coming to eat our lunch. One of the things that's really needed for reality to work right is that dark matter. It causes galaxies and stars to clump together. Now, nobody has actually ever seen a particle of dark matter, but we have a lot of indirect evidence that dark matter exists. A Nobel Prize has been awarded for dark matter now because the amount of evidence is so overwhelming at this point. But dark matter is a reality. We just haven't seen it directly yet, and it is essential for our reality. A more definitive thing is the Higgs field. This was hypothesized 50 years ago, and the Higgs boson was actually detected about 6 years ago, and received a Nobel Prize. And that is indicative that the Higgs field exists. The Higgs field interacts with particles to give them mass. Without the Higgs field, everything would be massless, and nothing would work right. So this is the 17 things, and that was a very brief rundown on how they contribute to our existence. Now, as I mentioned before, the thing that got me started was the fact that protons don't quite stick together, but they do. They stick together for 1/100th of a trillionth of a second. 1/100th of a trillionth of a second. But you know, if they stuck together for 1/1,000,000th of a second, that would be very, very bad, because instead of the sun living for 10 billion years, the sun would only live for 1/10 of a billion years, and it would have died a long, long time ago, and we would not have had time to evolve. So the fact that these protons only stick together for a very brief amount of time is essential to our existence. And I'll explain why shortly. So in the sun, due to thermal agitation, these protons bang together, they stick for 1/100th of a billionth of a second, and most of the time they fly apart. But every now and then, one of the protons turns into a neutron by emitting an anti-electron and a neutrino by what's known as the weak interaction. As the proton turns into a neutron. And now, instead of having two protons temporarily stuck together, you have a deuterium nucleus that is heavy hydrogen. This is the first step on fusing hydrogen into helium in the sun. This is the very first step in getting that fusion process started. So the fact that these protons stick together very briefly is critical in this first step of producing deuterium and getting the process of fusing hydrogen into helium going in the sun. And again, if that lifetime of this helium-2 unstable nucleus were a little bit different than it was, if it were a little bit shorter, then the sun's lifetime would be reduced, and we would not have time to evolve. When I heard this, it knocked my socks off, and it got me thinking about this kind of thing, and I've been thinking about it ever since. Okay, this slide now goes into the four forces. Gravity, as I mentioned, holds the Earth in orbit around the sun, and it has a 1/r² dependence on distance. Newton identified this as essential to our existence and took it as providential. I'll discuss that some more later. The electric force holds atoms together. Electrons stick to nuclei, and this holds atoms together. It also is important for electricity flowing in wires. The strong force holds nuclei together, like those two protons that were sticking together. There was a nuclear force that sticks them together. The electric force is pushing them apart, but the nuclear force sticks them together. The weak force changes quarks into their siblings. And as I pointed out in that reaction where one of those protons turns into a neutron, that's the first step in getting fusion going in the sun. So it's the weak force is essential for building up complex nuclei in stars, changing protons into neutrons so that hydrogen in the stars can build up complicated elements. Then, the strength of the weak force and the strong force are critically balanced so that you end up with long-lived stars like our sun that are throttled in a way that they can produce 10 billion year lifetimes and enough time for people such as ourselves to evolve. One of the things that the weak force also does is it helps these very big stars blow up, because right at the end of their lifetime, when they collapse into a neutron star, they emit a huge flood of neutrinos, which interacts with their outer layers and helps the outer layers blow away. Another thing that the weak force does is it provides a radioactive decay for a lot of our geothermal energy, which keeps the Earth hot and keeps volcanoes going, emitting carbon dioxide, keeps the ocean working right, and plate tectonics working right. Now, one of the things that was found out recently was that the weak force combines with the electric force at an energy of about 100 billion electron volts. And this has been proven experimentally, and it's received Nobel Prizes. And the fact that these two forces combine into a single force called the electro-weak force at a very high energy got people thinking, well, maybe the strong force also combines with the electro-weak force into a single force, and we'll call that the gut force, the grand unified force. And if you extrapolate these forces, you figure out that the energy where they would combine is 10 to the 16th billion electron volts. This is an energy that's about 1,000 trillion times higher than what we can produce today in accelerators. So any theory of the gut force is highly speculative, and so it's very uncertain what exactly goes on at this energy level where the gut force has combine the electric force with the strong force and the weak force. One of the things that happens here is that in the Big Bang, this is where the imbalance between the antimatter and matter occurred. That is where you ended up with 1 part per billion excess matter over antimatter was operative at this particular energy, and exactly what happened there remains to be discovered. Now, if you go to even higher energy, you can combine this gut force with the gravitational force into a single force and generate what are called theories of everything. These are TOE theories, theories of everything. And 2 broad categories of them are string theories, which propose fundamental objects which are microscopic strings that operate in extra dimensions. We have normal 3 dimensions of space, but in addition, the string theories propose 6 or 7 extra spatial dimensions that are compactified, where that you can traverse in those directions by about a trillionth of a trillionth of a trillionth of an inch. But that's as far as you can go. That's the length of one of these strings. And these strings rotate and vibrate in those extra dimensions and produce the effects that we call elementary particle physics. Anyway, that's what the string theories are about. And they're highly speculative. They're at energies where we can't explore experimentally. So it's going to be a long time before anybody can nail these down. And right now, there's a potential for something like 10 to the 500 different candidate string theories. Each one of these represents a different potential universe. And maybe only one of those 10 to the 500 universes is the one we've got and the one that would actually work in terms of producing intelligent life. Some string theorists speculate that only one of these 10 to the 500 universes could produce intelligent life. And maybe we got the one in 10 to the 500 that works. Another TOE theory is what's called loop quantum gravity. And this proposes that space looks like chainmail, where you have these quantum loops that are all linked together. And these loops then can generate 3 spatial dimensions plus 1 of time if you put in causality. Okay, now I want to talk a little bit about gravity some more. Newton figured out that the gravitational law was dependent on the square of the distance from the object, and this would produce stable planetary orbits. He took this as providential, that we had this gravity law because it was essential for our existence. Reverend E.M. Paley also took this as evidence for a designer. Immanuel Kant figured out that the fact that this law is 1 over r squared is due to the fact that our reality is 3-dimensional. In a 4-dimensional universe, it would be 1 over r cubed. Well, if we had a 4-dimensional reality and a 1 over r cubed law, orbits would be what's called metastable. It wouldn't actually be stable. If you didn't have exactly the right amount of velocity for an orbit, this is what would happen. If the velocity were off by 1/10 of 1%, after 2.5 years, you'd spiral out by 50% from where you started. And that's only being 1/10 of a percent off. It's like trying to stand a pencil on its point. You just can't do it. So 4-dimensional reality does not work. You cannot get stable orbits in 4 dimensions. Now, in 2 dimensions, you can get stable orbits, but you can't get complex chemistry in 2 dimensions, most likely. And you certainly couldn't get intelligence in 2 dimensions because you couldn't have crossover straps in your neural networks or your electronic circuits. So 3D reality is the only one that works right in terms of producing intelligence life. Okay, this slide here shows the timeline of the Big Bang. Here we are 14 billion years after the start. We have galaxy clusters, large galaxy clusters that are very uniformly distributed throughout space. And we have an expanding universe where if you look out, everything is expanding away from us at a rate that is just right to expand forever. We call that flat. Now, if you reverse the expansion process, you extrapolate back and you say, well, it all emerged from a single point at some distant point, distant time, 14 billion years ago. And so you go way back, and if you go back to a trillionth of a trillionth of a trillionth of a second, a theory called inflation was proposed to explain the uniformity of matter and the flatness of the universe. The idea of inflation was that the energy of the universe, when it converted into the gravity and the gut force, that it also produced an inflaton field that had energy in the field. The fact that this field energy existed turned gravity inside out, so that gravity became a repulsive force that caused the universe to double in size every trillionth of a trillionth of a trillionth of a second. These doublings occurred over 100 times, resulting in a smoothing out of the universe, making it very flat and uniform. And so that accounts for the fact that it looks the same in all directions and that we have a flat universe. Then at the end of inflation, the inflaton energy, the energy in the inflaton field converted into the particles of our reality, and the expansion continued on by ordinary Einsteinian general relativity for 380,000 years, and all the time cooling down and expanding larger and larger. When it cooled down to about 5,000 degrees centigrade, the electrons started attaching to the nuclei of hydrogen and helium that were around and forming atoms. And this plasma, this glowing plasma that existed up until then, ceased to exist, and you just had dark atoms, and you entered a dark age when there was no light being produced anymore. And for 100 million years, there were just a fairly uniform distribution of atoms that were gradually clumping together over 100 million years to form the first stars. When those stars lit up, there was light again in the universe, and those stars and galaxies started evolving to more and more complicated structures that we see today. This slide here goes into some more detail on the inflationary theory. It turns out that in these inflationary theories, there's a larger meta-universe that is inflating to this day. And it's continuing to double every trillionth of a trillionth of a trillionth of a second. And that there are sub-universes, pocket universes, where inflation has ceased, zillions of them. And in each one of these pocket universes, the laws of physics are different, because when these pocket universes spawn out of this inflationary milieu, they each generate a different set of physical laws by the way this fundamental force field fractionates into the four forces. It can spontaneously change into these sub-forces in different ways in each one of these different universes. So many of these universes don't have any matter in them at all, any excess matter. There was an exact balance between matter and antimatter, so there was no excess matter. You don't have any stars. and they're just dark, uninteresting places. Here we have a universe such as our own that has long-lived stars, and we like it like that. Over here, you have a universe with short-lived stars that are only exist on the boundary where inflation has ceased. In the deep old interior, there aren't any stars. And in most of these universe, nothing interesting is happening. Only in one universe in a zillion is anything interesting happening. Another way of expressing this is to imagine this field of snow here, and only the crystallites that are reflecting light green light are the universes with intelligent life. There it is, that's the one. The rest of them are not doing it. Most of them aren't even producing light because they're buried underneath the snow where they can't produce any light at all. One of the reasons for thinking that the inflationary theory might be the right way to go is this image of the sky taken with a microwave telescope. If you look up at the night sky with a microwave telescope, this is what you see. And what you're looking at is the light that was emitted just before the universe went dark when it was 380,000 years old at a temperature of 5,000 degrees centigrade, when the atoms were first condensing. And the light that was being produced at that time was visible at that time, but the universe has expanded by a factor of 1,000 since then. So the wavelength of that light has expanded by a factor of 1,000. So instead of being a micron in wavelength, which is something that we could see, it's a millimeter in wavelength, which is something we can't see. It's what a microwave telescope can see. And so this is what you see. And these are hot regions of the sky, and these are cold regions. These regions are 1 part in 50,000 hotter than the average. These regions are 1 part in 50,000 colder than the average. And these regions will become galaxies and stars and superclusters of galaxies. These regions will become voids where you get nothing.
Homemade masks are not personal protective equipment.
Anyway, this variation in density and temperature is predicted by the inflationary models. The variation, the inflationary models predict that quantum fluctuations at the beginning of inflation get magnified by inflation and blown up to be these fluctuations that we see in the sky today. These tiny quantum fluctuations at the beginning of inflation are now tens of billions of light years across, or hundreds of billions of light years across in the night sky. It's at any rate, it's one of the triumphs of the inflationary model that it can fit the variation in density of this image. As I mentioned before, it's essential that big stars blow up. And this is a picture of a big star blowing up. This is supernova 1987. It was detected first as 22 neutrinos in 3 separate sites on neutrino detectors on Earth. The fact that there were 3 detectors allowed them to triangulate the source and notify the astronomers as to where to look. And they looked and they were able to take this picture of the supernova explosion. The fact that these neutrinos this flood of neutrinos occurred as part of the supernova explosion confirmed the theory of exactly how these big stars blow up, and the fact that that the process is critically dependent on the weak interaction producing this flood of neutrinos. So after billions of years, big stars blow up and seed galaxies with complex matter. and medium-sized stars, second-generation stars, and planetary systems form with rocky planets with water and heat from residual heat from their condensation and the radioactive decay, combined with the chemistry of the rocks and the water, provide energy in the form of food for microbes. Somehow muck made microbes. We don't know how. This is one of the great mysteries. It may have happened here. It may have happened elsewhere, and the microbes got transported here. That's called the Panspermia Hypothesis. Lord Kelvin was a subscriber to that. One of the mysteries is the fact that we have fossils of single-celled microbes within 500 million years of when the ocean first formed, which is a very short amount of time. And it's problematic, I think, that, that such complicated things as microbes could have evolved out of a simple chemical soup in only 500 million years. So I actually favor the Panspermia hypothesis. Anyway, microbes evolved individual and complexive and collective complexity. They started to link together to form complicated multicellular organisms, initially sponges, but then more complicated things that could move and needed nervous systems and brains. These brains evolved to higher levels of complexity as time went on and started communicating and interacting and formed collectivities of mind, which I call noosphere. This business of collectivity of mind got a huge boost in humanity with our technologies of communication, first with language between 50 and 200,000 years ago. Nobody knows exactly when human language got going. Writing got going about 5,000 years ago, printing a few hundred years ago. Electronics and telegraph, phones, radios, all modern stuff now. And ultimately, we'll be able to use radio to communicate with extraterrestrials at some point. We don't have a monopoly on this communication thing. Elephants, chimpanzees, and dolphins all communicate with their. These are mammals. They teach their young how to find food, and they're all good mothers. The chimpanzees use sticks to probe for termites. They use nuts to crack, rocks to crack nuts. This dolphin uses a sponge on its nose when foraging in the gravel for crustaceans. It learned this behavior from its mother. The mother taught all its daughters and some of its sons to do this. This is an image of the night sky showing 3,000 galaxies in an area about the size of a tennis court viewed at a distance of 100 yards. So if you extrapolate this to the entire sky, you calculate that there's almost a trillion galaxies in the sky. And each galaxy has almost a trillion stars. So there's almost a trillion solar systems, because recent studies indicate that every star has a solar system. So there's got to be other intelligences, civilizations out there. It's just a matter of statistics. Trillion potential sites. So see if you can think of when this was said. When there is plenty of matter in readiness, when space is available and no cause or circumstance impedes, then surely things must be wrought and effected. You have a store of atoms that could not be reckoned in full by the whole succession of living creatures. You have the same natural force to congregate them in any place precisely as they have congregated here. You are bound, therefore, to acknowledge that there are other regions, that in other regions there are other Earths and various tribes of men and breeds of beasts. So, think to yourself when this was said. You can't call it out. Anyway, it was said in the 1st century BC by Lucretius. He was a disciple of Democritus, who was a 5th century BC philosopher. Now, the philosopher Giordano Bruno was burned at the stake for advocating this, and in 1600, along with other heresies like the Copernican heliocentric theory of the solar system. So my question is, are the ETs out there like the inquisitors that burned Bruno at the stake? I think not. The average high-tech civilization that's out there is way ahead of us. The chance that they're at the same level of technology that we're at is zip. That is, they haven't just started technology the way we have. If they're into high tech, they've been there for a long time. And so if they've been there for a long time, they've had to live with a bomb for a long time. It's a kind of Nazi filter. It's a test of who they are. They have to be fairly Gandhi-esque in order to live with a bomb for a galactic time scale. It's the cosmologist Edward Harrison in his book Cosmology calls it galactic selection. I called him up, we discussed this, we were exactly on the same wavelength on this. It's a filter for civilizations. Any civilization that's out there has been subjected to galactic selection, if they're still there. The big question is, will we survive galactic selection? We have almost failed about 5 times since the Cold War began. We've had 5 close calls at least with nuclear holocaust. And so the question is, would they talk with us? And I think not, because we have to pretty much get through this on our own. We have to prove that we can survive galactic selection on our own. And I'm talking about thousands of years, not a few decades. And they have more to fear from us than we from them, because even though their technology is zillions of years ahead of ours, our culture is zillions of years behind theirs. And so we are scary. If we get their technology, they have to watch out. And this is proven by another quote, ancient quote. And this one is attributed to Alexander the Great. Okay. Alexander wept when he heard from his friend Anaxarchus that there was an infinite number of worlds. And his friends asked him if any accident had befallen him. He returns this answer: "Do you not think it is a matter worthy of lamentation that when there is such a vast multitude of them, we have not yet conquered one?" So if the ETs have read Plutarch, they're going to stay the hell away from us. So how could 17 cosmic stepping stones to intelligent life have any likelihood at all of coming into existence? There's 2 hypotheses on this slide. One is the most common belief, that is a deistic hypothesis. That is that a creator worked hard to set a stage where the raw energy of the Big Bang could evolve into dramatic beings like us. In this case, life has derived value. But what is its value or meaning? Ask a prophet. Which one? Ugly disputes have occurred. Is the value for us to find and create? Is it an exercise for the reader? Was galactic selection part of the design? I claim that I can prove that it was, because I can prove that if the electron charge were 1/3 of 1% higher than it is, we would live in a nuclear-free universe without galactic selection. That is, if there was a deity, the deity had the choice of giving us a nuclear-free universe and chose not to. The deity chose a universe that had galactic selection. In other words, either live with galactic selection or get the hell out of the universe, one or the other. Either become Gandhi-esque or get the hell out of the universe. That's the way it is. That's the way the deity wants it. If you believe in a deity, you have to believe that that was what was stuck in your face. Okay, the other hypothesis is known as the Anthropic Principle. In this hypothesis, you propose that somehow a zillion universes came into being one way or another, either through a multiverse that had a zillion pocket universes in it, or a sequence of generating universes one after another, whatever. There had to be a zillion throws of the dice, each with different physical laws in the universe. And somehow we got this one universe in a zillion, this rare gem with just the right laws such that it could produce witnesses such as ourselves. We have the one in a zillion with spontaneous creativity built into it. Our improbable universe and its life has inherent value. It's got all this built-in creativity. It's a wonderful place. It's incredible. So I contend that the conclusions are convergent for these two hypotheses. It's the same either way. Life is valuable, and creating value is an exercise for the reader. We are working on it together in an ongoing creative process. And that's my talk. Thank you for your attention.
I guess we'd like to try to do some questions now.
All right. Okay, first of all, I'll do the last one here. It says, I found the lumpiness fascinating. What are the current scientific hypotheses, or what is the general consensus as to why this happened? Well, as I was stating, the lumpiness, according to the inflationary model, occurred as a result of quantum fluctuations at the beginning of the inflationary period. In quantum mechanics, there's always fluctuations going on all the time. But these quantum fluctuations are very tiny. But inflation, it caused these fluctuations to be blown up to huge size so that they span many hundreds of billions of light years. And so that's one of the hypotheses as to how that lumpiness got generated. It does, okay. And so that's answers that particular one. Then there's another, okay, then there's a comment. It seems like to me that civilizations have a life cycle that is shorter than its planetary origin, or that the evolution of civilizations exist at a close enough time to actually interact at all. Well, I don't think that there's any law that says civilizations have to die. I think that, we can take control of our own fate and do what we want with it. If we want to be idiots, we can flush it down the toilet. If we want to be sane, we can save ourselves. But, it remains to be seen what we're going to do. Anybody want to ask any more questions?
There's a question from Charles Robinson.
This is Charles.
Okay, what's your question, Charles?
Well, one of my favorite coincidences is that water gets denser as it gets colder. And the curve of density, when it gets to 4 degrees, just 4 degrees above zero, it turns around. That's a funny coincidence. And if that little curve wasn't there, lakes would freeze from the bottom up and we wouldn't be here to talk about it.
That's right. Yeah, that's an interesting thing. And there's a book called Rare Earth that talks about a lot of things associated with just planet Earth that were essential for us to have come into existence, that Earth had as a property. And now water is one of those things too, but we could probably come into existence without this particular property of water you know, but it certainly has helped. Yeah. And yeah, and it is counterintuitive. Most materials don't behave that way.
Okay, we have a chat question from Stuart.
Okay, it says, what convinces you that there has been enough time for that many super advanced civilizations to have evolved? Well, the thing is that our you know, our particular evolutionary process has been going on for about 4 billion years. You know, the universe is 14 billion years old. So we've only been working on this for a tiny fraction of the life of the universe. There's been plenty of time for other civilizations to have gotten going long before us. I mean, you know, that the civilization, you know, something like us could have started within, you know, a 500 million years after the Big Bang, and not 10 billion years. We didn't have to wait 10 billion years before we started evolving.
Okay, Mike, F is asking the question, can some universes be contained in other universes?
Yes, I would imagine so. You know, I don't really, you know, this is all very speculative. You can imagine the inside of a black hole, for example, being a universe within a universe. You know, it would, the inside of the black hole would be a universe that you would not have access to, but there is something in there, you know, and whether or not it's a universe or what it is, you don't know. I mean, but that's, you know, a kind of example of a universe within a universe.
Okay, here's a raised hand from Charles Robinson. He's going to ask a question.
Okay, thank you. Why would all these coincidences have happened? And the answer that I understand is called the Anthropic Cosmological Principle. Does that play a role in your thinking?
Oh, yes, of course. Yeah, the Anthropic Principle is just saying that these coincidences had to happen, you know, otherwise we wouldn't be here to witness it, you know, so.
Well, along with the fact that, as Tad Tryon wrote in 1974, the universe is one of those things that happen from time to time. That the universe a universe will pop into existence as long as all its quantum numbers are the same as that of the vacuum, just the way an electron-positron pair can pop into existence.
Well, yeah, that's speculative. Nobody really knows, you know, how universes come into existence, nobody really knows. And you know, that's getting very speculative when you start talking about that. And how do you get a zillion universes? Nobody knows. It's speculative, okay? And this occurs at energy levels where we don't have the machinery to generate those energy levels. So you can't call it science because you can't test your hypotheses. You know, it's getting very speculative. But one thing you do know, though, that I can identify 17 things that had to be more or less the way they are, and other scientists can add to the list. We know that there are a lot of things that were essential for us to have come into existence. And therefore, if we arrived at that process by a random happening, then it took a huge number of throws of the dice for it to have any probability of getting these 17 things lined up. You had to throw the dice a zillion times.
Mike, there's a chat question from Jim Everett. How could we have evolved in the first 500 million years if our chemical components are dependent on protostars developing and blowing up.
Right. Well, no, we could not have evolved in the first 500 million years, but the process could have started 500 million years. That is, the 500 million years after the Big Bang, big stars started generating heavy elements and started blowing up. So in principle, you could start getting second and third generation solar systems within 500 million years of the Big Bang. So, you know, that evolutionary process could have gotten going 500 million years after the Big Bang had occurred. It didn't have to wait 10 billion years before, you know, it started producing a solar system. It could have produced a solar system 500 million years afterwards. You know, so I'm just saying that there was plenty of time there for solar systems to have gotten going a long time ago. You know, we're really Johnny-come-lately on the scene, and so I expect that yeah, there's extraterrestrial civilizations all over the place, because you know we're really latecomers.
All right, I'm going to close the meeting, and I'd like to turn it over to Pat. And thank you, Mike, for your excellent talk. And Pat will say some closing words.
Thank you. Can you hear me?
Yes, I can.
Good. Thank you, Mike. You gave us a splendid talk and discussion. It'll be a great evening to think back to, and we remember our small group's first humanist video conference on the internet, meaning this. In future, we can have participants not only from anywhere in the US, but even from anywhere in the world. You heard one of our Australian audience members ask a question, and so that demonstrates that we really are more than just US, but we can go anywhere in the world, because where he comes from, Perth, Western Australia, is as far away as you can get on the Earth. Well, thank you all our guests who helped us by coming this evening and making it work. We wish you all health and security in these difficult times. Thank you, everybody, and good night to you all, and blessings. Bye.
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 Right.